So, welcome at the next lecture. Is it running actually? It is running, okay. So, today we are going to talk about an important topic. Unfortunately, this topic will not be directly related to what we will do in the afternoon, because the semestral or the lab exercise related to benchmarking will happen later, because it's exercise related to Java, and Java part will start later. But nevertheless, I will cover many topics which are general, which could be useful like to your last homework and to any other activity related to benchmarking that you will do not only in this course. So first we will start with a brief introduction, like what it is benchmarking, how we can approach it, and then we will talk about like big chapter, how to measure timing and how to summarize the results of the measurements, because this is like one of the most important part in benchmarking of computer programs. Typically, we are interested in whether some of our change in our code resulted in some kind of speed up. We want to make our program faster, more efficient. So lastly, we will talk about how to actually measure and properly calculate speed up, so that we are really sure that our program is really faster. So let's start talking about benchmarking. Benchmarking, I guess everybody here knows what I mean by that, but just to repeat, benchmark can mean two things. The first thing, and that's what this lecture will be about, it's the act of running a computer program, and we want to assess some performance, and the performance can be of the definition, I think from Wikipedia, is that the performance can be about an object, and by object we mean typically some hardware, some algorithm, or a compiler. So here we are talking about efficient software, so we will talk about like benchmarking software, which means either algorithms, programs, applications, and so on. The other meaning of the word benchmarking or benchmark is like the program which performs this this measurement, this assessment. So you know there are some well-known benchmarks for whatever you are interested. GPU performance and whatever, so we are not going to talk about specific benchmark, we will talk about what's behind it. Whenever we are benchmarking something, it's important to distinguish two basic types of benchmarks, like micro benchmarks and application benchmarks. When you want to make something faster, it's usually easier to start with micro benchmarking. So you take one simple function in your program, a really small piece of code, and you measure these improvements in this small piece of code. This is quite easy because the thing you are measuring is small, easily handled by benchmarking tools and whatever. But the rule to remember is that even if you have some improvements in micro benchmarks, it doesn't necessarily mean that it really improves the whole application, because typically applications are much more complex than just a single algorithm, single function, single whatever. Applications are complex, and the performance of the application depends on many factors. Not only the algorithms, but also the operating system, file system, networks, and I don't know what else. So it's a common mistake that people do. They say, oh, I have improved this micro benchmark by 10%, hence my application will be 10% faster. But if someone measures the whole application performance, it can even happen that improvement on one side make the whole application slower. So be careful about things like that. So the next question, the most important question, is how to actually measure a software performance. So there are many things that we can measure. Execution time is probably the most important thing, and most of this lecture is devoted to measuring execution time. But also you might be interested in reducing or improving memory consumption or energy consumption. So we will briefly talk about these later. The question is now how you can measure these things. And as you will see, it might not be that easy as it sounds. Even measuring like how long does it take to execute this function can be quite difficult, quite challenging, because we have this hardware which has a lot of caches, and you measure your execution time several times in a row, and every time you get different results. So how to deal with that? The same happens with memory. The memory is shared by not only your program, but also the operating system, other programs, and actually precisely measuring the memory consumption can be tricky in some cases. So it's necessary to understand like what you are actually measuring and what the numbers that you are seeing actually mean. And energy, it's another thing. In the end, a big part of this lecture will be about statistics. Usually people who studied physics, they have quite good understanding of uncertainty and how to use statistics to make the measurements more precise and reliable and so on. But typically computer science people or computer engineering people, they do not like statistics, they do not like measurements, they think that computers are completely deterministic, and some non-deterministic nature of measurements is like foreign thing to them. So we will just look at how you can use statistics and why you actually need statistics, even if you deal with computers which you might think are deterministic, but from the performance point of view are not really deterministic. Yeah. So now we will look at briefly at how to measure this memory consumption, energy consumption, but then the biggest part of the lecture will be about execution time. So let's start with the easy thing, which is energy. How you can measure energy consumption of your program, of your mobile phone, whatever. Just plug it to some power supply, use some power meter, plug it together with your power supply to your mobile phone or whatever, and measure it. That's easy. What's not easy is that you will see a lot of spikes in the measurements and so on. So you will have to do a lot of averaging and so on. And also, computer science people do not like wires and messing up with additional tools and so on. So nowadays, many commonly used platforms, hardware devices, they already have some power measurements built in. So for example, Intel CPUs, they have a piece of hardware which is called Intel RAPL, running average power limit, which is something like performance counters that we have talked about before, but those actually measure the power consumption of different parts of the chip, like of the memory, of the CPU, and so on. And you can use the values read from those registers to somehow decide what your program can do and so on. So you know it very well from your mobile phones. You can see in your phone like which applications drains your battery the most, and this is typically implemented by hardware with features like this. So that's the easy thing for energy. Now a bit less easy thing is how to measure, how to benchmark memory consumption. The thing is that there are many ways how your program can consume memory, and typical profilers and other programs, provide only a subset of those ways. So the most easy way how you can measure memory consumption of your program is to actually measure how much memory is consumed by your process in user space. This means like the memory used for storing application code, application data, heap, stack memory, and so on. So this is very easy because every operating system makes it easier to measure how much the size of this data, but unfortunately this is not all memory which is actually used by your program, because at the same time your program probably uses some kind of operating system kernel services, and those services inside the operating system kernel use some memory as well. So typical example is networking. Whenever you do some kind of networking, there are some memory buffers related to networking for handling receiving and received and sent data from the network. And this memory is not allocated inside your program. This memory is allocated inside the operating system kernel. And typically, all programs running on your system somehow share this memory. So without some additional digging into the operating system, it's not that easy to figure out how much memory is consumed by your program in networking buffers or in disk caches or in, I don't know, whatever else is used by the operating system. In some cases, this is not important, that memory is small, but if you do, I don't know, like heavy networking application or database applications and so on, this memory can be like big proportion of the actually used memory by your application. And the last thing which might be a bit tricky is handling of shared libraries. So shared libraries, as the name suggests, means that a single library is shared between multiple processes, multiple programs. So the memory, at least the memory needed for storing the code, is actually shared by multiple processes, but the data is typically not shared. The data is allocated to a single program. So if you want to understand how much memory does your application consume, these are all things that you need to be aware. And now, very briefly, whenever you I will talk about Linux because this is what I know most, but in similar or other operating systems, things are a bit similar. So if you list the processes under Linux, typically tools like top or htop report memory statistics under the three different names. First memory statistic is usually called virt. It's a short for virtual memory, and this reports how much virtual memory is allocated by the application. As the name suggests, virtual memory is not real memory, it's just virtual address space, and there is no guarantee that this virtual address space actually contains any physical memory which can be used by the program. So it can be, so if you look at just these numbers, virtual memory, this is usually the biggest number, but this number is not really related to probably what you are interested. This number just says what is the size of the address space currently allocated, and if you want to experiment a bit and see how imprecise this can be, you can, if you write an application in C, you can call a system call like this, which tells the operating system to allocate virtual memory without allocating any physical memory. And for example, you can do this this one shifted to left by 34 bits, it means like 16 gigabytes of memory. You can do this on a computer with much less memory, like, I don't know, 4 gigabytes, and this will succeed. It will just allocate some page tables which point to nowhere, and this virt value in top or htop will point or will report like 16 gigabytes, but your program is not using that. A more realistic number of memory usage is this res value. This stands for resident or physical memory, which is used by your program. This is actually the memory allocated in the address space of your program, but this is only the user space memory, and this corresponds to what your program uses, but this excludes this shared memory, which is the memory also in the user space of your program, but shared with other data. So if you are interested in memory consumption of your process, you need to take into account this resident memory, and depending on how you deal with shared memory, you can either count up this shared memory or you split this shared memory with all the other programs that use the same libraries and other sharing. It depends on you. So this is how we can get some information about or some kind of, let's say, overview of memory. If you want to see more details about how actually your program uses your memory, it really depends on memory allocators and system that you use, and you will see how Java does that, how Java can help you with profiling memory. Similar techniques are for C++ and native programs as well, but there are really many options, and depends actually on which memory allocator, which system do you use. So this was in a nutshell about how to measure the more easier part, and now the main topic of the lecture is how to measure the time spent by your program. We have already seen the performance counters. We have already seen that we can use performance counters to measure like cycles, but spent by your program, but this was just for the whole program. Now we are interested in measuring, for example, how long does a single function take, and so on. And to do that, we need to add some timestamps to our code. For example, at the beginning of the function you take a timestamp, at the end of the function you take another timestamp, you subtract the timestamp, and then you see how long the function took to execute. It sounds easy, but it's not that easy, at least in some cases. Because if I say timestamping, there are actually multiple ways how you can get timestamps. Some ways are very efficient, but maybe not reliable, maybe not precise. Some things are less efficient, but more reliable, and so on. So it's actually necessary to understand how timestamping works and to be sure that you are using the right timestamping mechanism available in your environment. So again, speaking about Linux, there are Linux system calls which allows you to call the operating system kernel, and the operating system kernel gives you the answer what's the current time. So you probably know functions which are actually system calls, get time of day or clock get time, which allows to do that. Those functions, if they really call the operating system kernel, can have quite huge overhead, because calling the kernel, calling a system call typically requires some hundreds of system or CPU clocks, like I don't know, 400 CPU clocks to make a system call on Linux, for example. On Windows it would be similar. There is no big difference. So the advantage is that it's easy, and the Linux kernel always gives you like correct result, because they know everything about hardware and they don't have problems that we will see next. But this overhead, hundreds of CPU cycles, it's a problematic. If you want to measure something which takes 20-30 cycles and the overhead of measuring time is 100 cycles, then you are not very precise in your measurements. Because people knew that for years, hardware designers tried to solve this. And every modern CPU nowadays has something which is called either timestamp counter or clock cycle counter or whatever. On Intel CPUs, there is always a register which is called TSC, which stands for, I think, timestamp counter register. And this is a special register which is read-only, and every clock cycle this register increases by 1. So if you read this register, then do something, and then read this register again, you can easily see how many clock cycles these other things that you have done elapsed. So how long does it take to execute that thing? That's nice. The overhead of reading this register is very small, so just reading this register in a loop, if you try it, you will see that you can read this register like, for example, every 8 clock cycles you can do one read of this register, so it's very efficient. But there are some problems with this as well. Nowadays, if you use modern CPU, those problems are more or less gone because hardware designers fixed those problems. But there are still older computers where there were problems in the hardware, in the implementation of this timestamp counter. So, for example, I said clock cycles. This register measures clock cycles, and you know that your CPU can run with high clock frequency or low clock frequency. So on some computers it really measures clock cycles, but you don't know whether on which frequency the CPU was running. So sometimes those clock cycles are nanoseconds, sometimes those clock cycles are half nanoseconds. So it's not actually time, it's just clock cycles. So it's difficult to compare that if you actually care about the time. Another problem might be that if you have multi-core CPUs, it might be that the timestamp counters on those different CPUs are not synchronized. And the operating system can migrate your thread between the CPUs. So if you start your function on one CPU, take a timestamp at the beginning of the function, then the operating system migrates your thread to another CPU, you read timestamp counter at the end of the function on another CPU, subtract it, you may end up with negative time. So it looks like your function executed negative time, which is of course impossible, but that's the effect. So if you use this hardware directly, this is typically what computer games and these things do, you should be aware of all those things and somehow deal with that. If you don't want to deal with that and you don't care about hardware incompatibilities and all the quirks of all computer architectures or microarchitectures, there is a third way, which is like the best of both worlds. It's called virtual system call, and how it works you can see on this slide. So the idea is that to read the time, you can use this timestamp counter, which you can read very quickly with low overhead. But the problem is that you don't know how does this number correspond to real time. So the idea is that you read the timestamp counter, and somehow you get some corrections how to convert this value read from the timestamp counter, how to convert it to real-time nanoseconds. So typically you multiply the number by some scaling factor and you add some offset, and by doing that you convert this time to nanoseconds, and this should work, or ideally this should work like on every hardware independently of whether the hardware is broken or whether your thread was migrated and so on. So how does this work? The only component in your system which knows the correct values of those two numbers, of those corrections, is the operating system kernel, because the operating system kernel decides which frequency your CPU is running, or at least if it doesn't decide directly, it has a way how to figuring that out. The operating system kernel knows when it migrates you to one thread or another thread, another CPU. So those values can only be known by the operating system kernel. So under Linux, those system calls like get time of day or clock get time, they are actually not implemented as a classical system calls that you really call the kernel, but they are actually implemented as functions, but those are not plain functions. In the address space of your program, there is an area of memory which is called VDSO, which stands for Virtual Dynamic Shared Object. SO, shared object, this is like a dynamically linked library, but this dynamically linked library is not, you cannot find it anywhere on your disk. This is a virtual library which is somehow synthesized by the operating system kernel, here by the Linux kernel, and from the point of view of the application, it looks like another library. Normal shared libraries are loaded from disk. This VDSO library is loaded from the kernel, and your program can just call functions from this library in the same way as as functions from other libraries can be called. And this library contains those functions like get time of day, clock, get time, and also there are variables which are automatically updated by the kernel whenever the kernel figures out that those values needs to be changed. So if you want to read, or if your application wants to read the current time, it just calls get time of day or clock get time. This goes to this shared library. The shared library reads timestamp counter, reads those values which are updated by the kernel whenever it is needed, do this multiplication, addition, and returns the time without actually calling the kernel, because the important thing is that this function is not inside the kernel, but it's in the memory of your process, and you can, it's just like function call. It's not a kernel call. If you are interested how actually it works, how it looks like, you can very easily verify yourself that it actually works, and you can see the code there. So for example, you can run your program in debugger. You can run that program, and you can see what is the process number of your run program. If you know the process number, you can look into the proc file system. In proc file system, you can see memory mapping of your process. And in that memory mapping, you can see at which address is this VDSO mapped. So you can find this memory range. This is where this virtual shared library is located. And then you can ask your debugger to store this memory range to some file, and then you can use this assembler to actually look inside that shared library. You will find that there is function which is called __VDSO get time of day. You can see what is the code in that function, and you will see that somewhere in the middle of that function there is a read timestamp counter instruction which reads the timestamp counter, and then you will see how it is multiplied by those correction coefficient and so on. So this is a trick which I would say normal operating system are using those tricks. So Linux, Windows, Mac, they all use these things. So actually calling clock get time of day, clock get time or get time of day is quite efficient on those systems. But if you use some other system, maybe some embedded system or some older system, calling clock get time can be quite inefficient, because it actually do system calls with all their overheads. So that's related to timestamping, and now we know how we can get the timestamps. Now what we can do with those timestamps and how to get some meaningful information from it. The problem that we are going to deal with to the end of this lecture is that whenever you measure some execution time, you will always see some variation. So you know it, for example, from your homework from last week, if you have already done that. If you have measured how long it took to execute this process image function, you would see that the variations of those numbers is pretty high. If you are, for example, interested only inside that function, that is this ransack function, if you were just measuring this the content of this ransack function, you would see that the difference is even higher. So highest is, I don't know, like 190, lowest is maybe 98. So almost like 100% of difference in measured time. So it's not easy to just measure this single measurement and this is my number. If you do this, you will definitely get some incorrect results. So the reason why this is the case is that there are many factors that actually influence this this execution time. So it's hardware. This measurement time depends on data, on the memory layout of your applications, on network load, system load, I don't know, whatever. So there are many factors. Some factors can be controlled. So if you do benchmarking, you probably want to understand those factors and be able to control them, and for those factors which you can't control, you have to do something about that, and this something is typically some kind of statistics. So if we take it graphically, we basically need to deal with the variations. To mitigate the effect of those variations, we basically have to repeat our measurement. So single measurement is never enough. You always have to repeat it. And we want to eliminate the influence of those random factors. So we use the statistics, and we want to control things which we can control, and we have to deal with things which we can't control, which are some random variables like hardware interrupts, the effects of the operating system scheduler, and so on. And then there are some uncontrolled variables which can make our results not correct. So how we will approach this? Whenever we are measuring some execution time, we cannot measure a single execution time. We want to measure what we will call mean execution time. And if you hopefully remember from statistics, mean is a property of probability distribution. So it's not property of the program, but it's a probability of probability distribution. The problem is that you don't know what is the probability distribution of your program. What you can do, you can sample this distribution. So you have some samples Those are the measurements obtained through timestamps. And from those samples, you somehow try to estimate what is the actual mean value. But because it's estimation, it's never like one single precise value, so it's always estimation. So it's important to know how precise this estimation is. And for that, we will use, or in statistics, people use what's called confidence interval. And the confidence interval, it's illustrated in this figure. So here you can see some probability distribution, and this is the mean value of that. This is normal probability distribution, so this is the mean value of this normal probability distributions. And then you try to sample from this distribution. So every line here is a number of samples taken from this distribution. So for example, it's like you take 10 measurements, you measure execution time 10 times in your program, and those are the samples that you will get from this distribution. You don't know this distribution, but you will get only those samples. What you will do, you will calculate the average from those samples, which is like the center of this red or blue line here. And you can also calculate those statistics, the confidence interval. So here, the confidence interval is written, or the confidence interval is marked with this horizontal colorful line. And this is what's called 50% confidence interval. What actually it means? If you have a 50% confidence interval, it actually means that the true mean is in 50%. If you repeat this experiment, it means that in 50% the true mean, which you don't know, will be inside this bar. So if this bar is red, you can see that the true mean is outside of the bar. If this bar is blue, it means that the true mean is inside this confidence interval. So, and as you can see, because this is a 50% confidence interval, you can see that there is approximately 50% of red things and 50% of blue things. This is the property. So normally, if you do some measurements, you are interested typically in 95 or 99% confidence interval, because you want to be really confident that what you have measured actually means what you are reporting. If you have confidence interval with for 50% confidence interval, it's too little. The result can be quite misleading, as you can see from this picture. Yeah. So that's confidence interval. The way how you can make the confidence interval narrow, because you are not interested, yeah, my program executes, I don't know, 100 seconds with confidence interval of plus minus 50 seconds, because it tells nothing. You want the confidence interval to be narrow, like 100 seconds plus minus 1 second. Which means that the confidence interval is between 99 and 101 seconds actually. Sorry, the execution time is between 99 and 101 seconds. So to make this confidence interval sufficiently low or small, you need to repeat the measurements. You need to repeat the experiments. And now there is actually multiple things which you can repeat. So for example, if you are measuring a single function inside your program, you can just repeat that function. But sometimes it happens that every time you rerun the program, the function runs differently, because maybe the execution time of your function depends on how is the memory allocated. Maybe if your memory allocator is not deterministic, if you run your program once, the memory is allocated somehow, the function is faster. If you rerun the same experiment next time, the result is different. Even if you repeat this function, this internal function, if you repeat the measurements, after different re-execution of your program, the result will be different. And not only that, if you run Java programs, which you will run in the second half of the course, you know Java has a just-in-time compiler. This just-in-time compiler uses some kind of profiling, which means that this just-in-time compiler can compile your Java program differently each time it is recompiled. So there is even some non-determinism in this just-in-time compiling. So the point is that you have to repeat things, and you have to repeat things at different levels, from iterations inside program through execution of your whole program, and maybe you have to repeat even a compilation of your program if you use just-in-time compiler or if you use a non-deterministic compiler. So yeah, that's what the next slide are about, and you will actually have some exercise about how to deal with that in practical terms. So we will talk about some theory, which, if you are going to write a research paper, you should somehow be aware of that, because otherwise everybody will laugh at you that you don't know how to measure things at computers. But not everybody here will write research papers and benchmarking programs, so I will give you also some more practical things if you don't want to spend much time with benchmarking and with statistics, so how to get some meaningful and useful results quickly. Yeah, so let's start with that. Let's say you measure you have some benchmarks, you measure some execution time or whatever, and you want to somehow summarize the results. So what you can do? The easiest thing, and perhaps the most informative thing, is to draw a histogram of what you measure. So here, this is some execution time. And as you can see, most of the measured execution times is, I think, yeah, I don't know what it is, but some kind of program. So most of the measurements happens to be somewhere here, but typical situation with computer programs is that there is a long tail of measurements. So most measurements is here, but there is a long tail. So one thing to notice from this is that this is not a normal distribution. So if you use statistics on computers, using everything just for normal distributions, it's not the best thing to do. On the other hand, you probably know there is the law of big numbers. So if you sum a lot of other distributions together, the result will be normal distribution. So, and we are doing a lot of measurements. So to some extent, these effects somehow, there is a trade-off between those things. So the thing is that if you blindly apply just a mean value, it might be that the mean value would be somewhere here, which is, as you can see, not a typical value. How does your program execute? So we want to summarize those values differently. So the good thing, or one of the possible things to do, is to calculate not only the mean value, but we also need to calculate this confidence interval, which tells us how precise this mean value is. If we have small confidence interval, it means like that this tail here doesn't have much effect. If the confidence interval is high, this tail, we didn't properly account for handling this tail. So this is what we will do in the next of the lecture. The second thing which you can do if you don't want to deal with calculations of confidence interval, you can simply calculate median. Median is pretty good statistics, and here the median would be, I don't know, here or here, something like that. So it would probably be pretty representative. But for research papers, it would not be enough. So for research papers, you need to do all the statistics properly. But if you are lazy, if you are hurry, I would recommend you to take the minimum measured value. Because if this is a normal distribution, it would not be good idea to take a minimum value. But this is not a normal distribution. Minimum value typically means that you have measured the result with minimum interference, minimum overhead, or whatever. So typically, computer programs have this. There is sharp minimum. It is execution time. There is no long tail to the left. And if you take minimum, it works usually pretty well. So yeah, so that's my recommendation. If you don't have much time for the homework that you will do like in 2-3 weeks, you will need to use proper statistics. Second technique which is used for or typically used in statistics is called significance testing. As you will see, the significance testing, every statistics course talks about significance testing. This technique is not very much suited for assessing performance of computer systems, but nevertheless people use it and sometimes it can be useful. What is it, significance testing? Typically you have your program, it runs at some speed. Then you make some improvements to this program and you hope that this improvement actually improved the speed of the program. So you have the hypothesis, this second program is faster than the original program, and this is the hypothesis, and then you can use this significance testing to verify whether the modified program is actually faster or not. Because as you could see from this picture before, let's go back to it. It can happen that the program actually behaves the same like this, but for the first time you have measured these samples and this mean, then you try to improve the program. Actually, you don't improve the program, you just do nothing, and then you measure this mean and this confidence interval. From those, if you just look at those two numbers, it could see, oh, I have improved it by this amount, but actually this is only insufficient statistics. If you repeat the experiments multiple times, you would see that you have not improved anything at all. So the significance testing just answers, is it possible that even though it looks like that my program is now faster, is it possible that it is just a coincidence that the statistics tells us that there is actually no speed up? And so there is a statistical theory. There is a computer program which is quite old, which is called Ministat. If I need to do some quick evaluation of some measured data, I'm using this program because it's very simple, very easy. Its user interface is not maybe as nice as you would like, but it works. The idea is that you just put 2 files of numbers to that program and it calculates those statistics here, and it calculates those confidence intervals and so on, and at the end it tells you whether there is a difference in the performance and what is the confidence of this difference. So basically the answer is yes, there is difference. One program is faster or slower than the other with 99.5 whatever confidence, or it says there is no difference at this confidence interval. So what's the problem? Problem is this approach. If you do this, and you know there is difference, it says just yes, there is difference, but typically you are not interested whether there is difference or not. Typically you are interested in like, is my program, how much faster is my program, like 10% faster, 20% faster, and so on. And for that, if you want to be technically correct, for that you need to use different statistics. And we will get to that, how to calculate the speed up of your program. We will get to it at the end of the lecture. So now back to the confidence intervals. If you want to calculate the confidence interval, you just look at some textbook, statistics textbook, or Wikipedia, or whatever. You find some formulas there how to calculate confidence intervals for different distributions of random variables. And for computer programs and for your homework that you will do in, I think, 2-3 weeks, you will probably use this kind of formula. So what it actually means: you measure several execution times, and you calculate the average from those measured times, and then all from those samples you will also calculate this value. So all of this can be calculated from the measured values. You take like standard deviation, you take some coefficients from some tables, you multiply it, add it, and whatever, do all these calculations, and then you will get this number. This is basically the confidence interval. So it's plus minus and some number. So if you are serious about your measurement and statistic, you should always report the results like, I have measured that my program runs 25.4 seconds or milliseconds plus minus, and this is the confidence interval. And it actually means that with probability of 95%, your program's execution time lies in this range. You don't know where exactly, but it lies somewhere in this range. So these are the numbers. Then what you can do with those numbers. The easiest thing is to perform so-called visual tests. So you calculate mean and confidence interval for your program before the change, and the same for your program after the change. And if the two confidence intervals overlap, it means probably there is no change, because it could be that there is a chance that the mean value is actually the same. But if the confidence intervals do not overlap, then it's a quick way to figuring out that there is significant change in performance, and your change to the program actually changed something. Speed up, we will talk about speed up, and Ministat doesn't calculate confidence interval, it calculates just the standard deviation. So just the recommendation: whenever you report results of benchmarks, do not report just a number, but always try to calculate the confidence interval. If you are lazy to calculate confidence intervals, you can also at least report standard deviations or something like that, because without some description of the variability of your results, the results are not really useful. So to summarize, there are some useful tools which you can use. So you have already seen Ministat tools. Some of you, I think I have shown it to some of you at exercise last week. It's a tool called Hyperfine, which allows to run benchmarks and automatically calculate those statistics for you, so that you don't have to calculate them. And finally, I will show it at the end of the lecture. I like Julia and its measurement package, and it can be nicely used for calculations with confidence interval. I have an example at the end of the lecture. So this was how to measure execution times, and how to do some simple or more complex statistics, how to report those execution times. One of the points was that we always have to repeat the measurements, and then from those samples obtained by repeating the measurements, we calculated those confidence intervals and mean values and so on. But, the next question is how many times we have to repeat the measurements. The point is that if we repeat the measurements not so many times, the confidence interval will be too wide, so our results will not be precise. If we repeat the measurements too many times, we are wasting our time, and the precision is not increased that much as for example necessary. So we have to repeat the experiment. And now we will look at how to do this repeating, how to and so on. So let's say we start with repeating iterations. There is some for loop in our program. So for example, there is this runSuck function in your homework, and this is executed 100 times or 1000 times and so on. So we are talking about things like that. Whenever we measure these values, we are interested in ignoring so-called initialization phase, because typically at the beginning of every measurement the numbers are higher than later. This relates to caching. When you run your program for the first time, the data or instructions are not in the cache, so first 1, 2, 3 iterations are typically slower. So this can be seen in this graph. So these are some measurements, and you can see that here at the beginning there are some higher numbers, and then it looks like the numbers are more or less random here, and there are no significant outliers. So good practice when benchmarking computer programs is to identify what's called either initialization phase or warm-up phase, and simply throw away the beginning of this data. So because the data are not independent, and this is some kind of artifact, and you don't want to use this with your statistic. The second thing is, or maybe I'll go back to the slide, we also want to reach the independent state where one measurement doesn't depend on previous measurements. If this is the case, all your measurements are independent, and if your measurements are independent, then most of the statistics are designed just for independent measurements. If for some reason your measurements are not independent and one measurement depends on the previous value and so on, then those statistics will be a bit off. So how we can figure out whether our measurements are independent or not. So there are two ways. You can, for example, use what's called lag plot or autocorrelation function. So what is a lag plot? Imagine you measure those execution times and you draw two-dimensional picture like this. Whenever you measure some value, you remember that value and let's say it was 2. Then you measure another value in second iteration, and let's say you measure this value like for first time you measured 2, second time you measured 2. So it gives you this point. So you are always taking like the current measurement and the previous one. And for those sequence of those consecutive measurements, you create 1 point. And then, if the measurements form some like picture like this, some ornament or some pattern which is doesn't look sufficiently random, this means that your measurements are not independent. There is some dependency. So whenever you measure let's say short number, then you can small number, then you measure wide range of numbers, and then if you measure this wide range of numbers, then you measure again some short numbers, and there are some patterns. It goes like up down, and so on. So this is not good. If you have like reasonable program, the result might look something like this. So it's not perfect. You see still there are some patterns, like there is no value here in the middle, but it's less random. It's less random than this. And this is a leg plot for one element. Similarly, you can do like you take current value and the last but one value or last but two values, and you create or you plot those leg plots for those different distances of measured values, and you should not see patterns like this. So this is a leg plot. The second option is autocorrelation function. This is probably what you know from statistics as well. If the values autocorrelation is that you calculate correlation between the sequences which are shifted by 1, 2, and as many samples as you want. This is the lag value, and the good autocorrelation function looks like that there is a big peak close to 1 for 0. Actually, it must be 1 because it's zero shift, and then for other lag values 1, 2, 3, the values are pretty small and somehow random. So this is like good independent measurements. If you see big peaks also for other shifts, for other lag values, this is probably a sign that the data are not independent and you have to change either the benchmark or the environment or whatever. There is something happening which would not work with the statistics. So some recommendations how to deal with that. Doing those graphs, this is a lot of work. So the idea is not to do it every time. You just do it like at the beginning to understand how does your program behave, whether things are independent or not. And if you have some basic idea about how your program, how your problems behave, you are no longer doing that and repeating that. So now, so far we have talked about repeating iterations in the program. Now I have said that another source of variance can be like at execution time. Whenever you execute, maybe some parts of your program use pseudo-random number generator, and you probably know that typically seed for this pseudo-random number generator is set just at the beginning of program execution. So depending on when you run your program, the seed is different, the random numbers generated are different, and this might have the effect on your program. Or even if you don't use random numbers in your program, you might have different input data of different sizes which somehow influence how which chunks of memory you allocate, and depending on which chunks of memory you allocate, the patterns of memory allocations where your objects are stored in memory can be different, and this all can have an effect on performance. So to trust me that this is true, this is from some paper which you will work with at the exercise. Those are some benchmarks which they performed, and they calculated what is the variance in different iterations in their benchmarks. And if they measured the variance of iterations inside the program in the functions, sometimes it's big, sometimes it's low, but yeah, there is some variance. But then they repeated the same experiments and looked at the variance not only within a single execution like here, but what was the variance between different executions. And you can see that in some benchmarks, the variance between different executions is similar to the variance in a single execution, but sometimes it's very different. For example, here, the variance was like 3% internally, and between different execution of the same benchmark program, the variance was like 30%. So there is really something important which depends on how when you execute the program or what happens during the execution, maybe at the beginning. So if this is the case, in your benchmark, you have to repeat not only inside the benchmark, but you have to re-execute the whole program to account for this. Fortunately, if you take this set of benchmarks as representative, you see that this is a kind of exceptions. All the other benchmarks behave reasonably, like those variations are approximately of the same size as the variations in iterations, but this is an exception. And if you want to benchmark things seriously, you should be sure that your application is not such an exception like this one. Yeah, so this is execution, and the second or the third possible where you need to repeat something is maybe compilation. If you have a compiler which is not deterministic, which, for example, whenever you use profile guided optimization, then your compiler is not deterministic, because actually the way how the compiler compiles your program depends on the profiling, and as you have seen, profiling is based on measuring, and this measuring is not deterministic. So if you use profile guided optimization, you have non-deterministic compiler, which means that you should repeat your experiments also for different recompilations of your program to be sure that you are not just lucky that your compiler just had a good day and optimized your code efficiently. Again, to demonstrate that the way how compiler can influence the variability of your experiments is in this graph. They used GCC compiler with all the optimization options set the same, but they did somehow change the linker, and they modified how the linker organizes the function. So normally the linker puts function in your code in the same way as the functions are stored in your source code. So they try to modify the linker, that they reordered the functions, so that the functions were stored in memory in different order than what they are in your source code, and repeated the benchmarks. And as you can see, that the layout of the code in your memory has some influence on repeatability of experiments. So in many cases, this reordering of the function causes some higher variations than what the compiler does by default. That's clear, because if you like do random things, that the variance will be higher. But the point is that even if you do some small change in your program, like adding one line or removing line or rewriting a single function, it can happen that maybe your code is laid out differently. Maybe the code doesn't fit into a single page. Maybe it has to go to another page because it's one byte bigger or whatever. And this results in some kind of effects that you think your program is faster, but actually it's just the effect of this reordering, or maybe some shifts in the layout of your program in memory. So this is also something to take into account. And now the thing, so hopefully you understand that you need to repeat not only iterations in your program, but in some cases you need to repeat also executions, compilations, and maybe even more. Now, and this section, this will be the point of your homework. So I think I'm not going to talk much about that now, because I think you will still need to read what to actually do in the original paper. So I will try to give you some idea, some notion, and what this homework will be about, and then you will have to read it yourself. So basically, we have to repeat the experiments at multiple levels: iterations, executions, compilations. We have to repeat them as many times so that we have reasonably small confidence interval, but we don't want to repeat them too many times, because we want to be done with the homework, with our work, and move on. And the idea is to figure out how many times we should repeat the experiments and find some optimum so that we get good results and don't waste our time. So there is some theory how to do it optimally, and there are some formulas, and yeah, so there is some notation. I am going to skip. I'm not going to explain all the formulas here, because yeah, it's not like that important. I will just show you the basic idea, what is it about. And the basic idea is that basically we want to know how many times we should repeat each level. So how many times we should repeat iterations, how many times we should repeat execution, how many times we should repeat compilations. And the idea how to calculate that is that if you imagine time is going from left to right, and this is like one iteration inside the loop of your program. Let's say this is some loop. So the idea is to calculate the cost of this iteration. So here the cost of this iteration, which is denoted as C1, is just the length of this single iteration. Now if you run this experiment, the code is not composed of just those iterations. Maybe there is some initialization code at the beginning, and maybe there is also some code at the end, or maybe like this, but I will just I don't have the I will just clean this one, because it would be easy to not have it. So to execute your program will execute some initialization and then your loop that you are measuring. So this is the second level of repetition. If you just repeat those multiple executions, you will always have this initialization and then those iterations. So whenever you repeat the execution, the cost for you, the time spent by re-executing your program will be just this. And then you can just repeat the executions. And at the same time, if you need to repeat also the program by recompiling it, the compilation time, compiling the program takes some time, so this will be the cost of compilation. So these things are the inputs to this analysis, to these formulas, and so you know how long, what is the overhead of every iteration at different level. You measure some times of those iterations here or here, and then you perform some calculations. This is some statistics. First, you will have to calculate what's called biased estimator of the variance at each level, which is calculated according to this formula. Then you obtain some value ti squared. And finally, you will just calculate confidence intervals like this. So you will calculate the mean value from your measured values, and then from the I think this is from the student t distribution, you will calculate the confidence interval base of those SN squared estimators. Yeah, so this is these are some formulas. The ideal outcome is that you somehow understand what those formulas mean and why they are needed. You don't necessarily need to understand why the formulas came to be and how they are, what's inside, but you should understand how to use them. So you can use those slides, or I recommend when you need it for the homework, you will probably need to look into the original paper where there is more explanations about what it actually is and so on. So to summarize this part, the recommendation is to, whenever you benchmark, you first at the beginning conduct some kind of dimensioning experiment where you measure these overheads of different levels of repetitions. Based on those overheads, you calculate the optimal number of repetitions, and then whenever you benchmark your results, maybe after improving some part of your program, you just look at, you just repeat the experiment that many times that you have just calculated according to this formula. Yeah, according to this formula. So this is the number of repetitions, and if you have this number of repetitions, then the confidence interval is calculated like this. Okay, and the last part of the lecture is devoted to measuring speed up. So as I have already mentioned, speed up is typically the thing that we are interested in. We want to say we have made our program to run 10% faster. How we can know whether it's 10% or 5%, we have to measure it, and since we are measuring it, it's imprecise. So we want not only to know how much faster the program is, but what is the precision of this number. And because this speed up is a ratio of two numbers, like the execution time of old program and execution time of a new program, or new version of the program, both execution times are random variables. The ratio of two random variables is also random variable with some confidence interval. So basically what we want to know at the end, we want to say our program is 10% faster with confidence 95 or 99% confidence interval of 2%, which means that with 99% probability our program is at least 8% faster, or it can be even 12% faster. So again, the question is how many times to repeat the speed up experiment, and the following slides gives us the answer. So imagine you perform several measurements of the old system, which we will denote y bar, and y prime bar will be the average of the new system execution time. If we have those numbers, we can measure the speed up this way, or vice versa. Different authors use different order of these values in this ratio calculation, and then you can calculate the confidence interval. So the confidence interval for the ratio of two random variables can be calculated this way. For this calculation, you use this value h, and this value h can be calculated again from some statistics tables this way. So if you want to be precise, which probably you don't need to be precise, you can use exactly those values and figure out the number of repetitions, how many times you have to repeat the experiments to reach this sufficiently low confidence interval. If you don't want to be that precise, you can use just an approximate formula for calculation of confidence interval, which is like this. And the whole point of this calculation is that it's quite easy to make mistakes. So the mistake is shown here. Let's say you have a program and you measure that the execution of your program is 10 seconds plus minus 1. So the confidence interval of your measurements is plus minus 1. So this means that the relative half-width of the confidence interval is 0.1. It's like 1 divided by 10. So this is this E here. So it's 10%. Now, let's say we improve our program. We measure, now the execution time is 9 seconds plus minus 0.9 seconds. So again, this half-width confidence interval, relative confidence interval, is again 10%. So nice. It looks like our program is 10% faster. But you calculate speed up, and if you calculate the confidence interval according to this formula, the result will be that the relative confidence interval for your speed up is 0.13, which means our speed up is 0.9 plus minus 0.13 with certain probability, which means that there is pretty good chance that speed up can be just 1. So it's not 0.9, but the speed up is just 1. So it means there is no speed up. So if this is our result, we have probably not improved the performance of our program. If we think that we have really improved the performance, we need to repeat the experiments more so that the confidence intervals are not like 0.1, but the confidence intervals are like 0.01 or something like that. And if we repeat the experiments that many times, and we get the result that the speed up is 0.9 plus minus 0.05, then we are happy. There is definitely some improvement. So lot of formulas, lot of computations. You need to look up tables and these things if you want to work with that. If you are lazy like me and you don't want to deal with that much, I definitely recommending the Julia programming language. There is a nice package used by physics. This is called measurements, and with that you can very easily calculate with confidence interval, and all these formulas which are here are somehow automatically calculated without you even knowing about those formulas. So with this package you can just use some like old speed up is 10 plus minus 1. You just type it to Julia like this, using these tricks to enter this plus minus, and then you simply calculate the speed up like new divided by old, and Julia will calculate the correct confidence interval for this ratio according to formulas like this. So the final recommendation, whenever you do some measurements and you report some kind of results, don't forget to report this effect size confidence interval for your results, because only in that case readers or recipients of your results will be able to trust you. Without that, this is just number without, nobody knows how precise it is. So to conclude, for the homework that you will do in, I think, like 3 weeks, I recommend reading this paper. So big portion of this lecture was based on this paper, all these statistics. The paper is called Rigorous Benchmarking in Reasonable Time. If you are going to, or if you want to write some benchmarking research papers, another good source of inspiration is a paper called Benchmarking Crimes. If you do, students often like doing benchmarking crimes, so if you want to write a research paper, definitely look at that so that you not commit benchmarking crime. That's all from my side. Are there any questions? If not, then thank you. You will probably have questions for your homeworks, but this will be next week.